Hello, today we're going to talk about ridge regression. The prerequisites for this material are ordinary least squares, our ordinary least squares coefficient analysis, and the analysis we did on the training and test error of ordinary least squares. Again, I'm going to use a motivating example where we're predicting the temperature in Yosemite from temperatures in other places in the US. So the response is Yosemite, and the features are the temperatures at 133 other stations. Okay, and then we obviously use a test set to evaluate. And here I'm showing you the coefficients of ordinary least squares for different numbers of training data. Of course, there's 133 coefficients, and that's what each of these blue lines shows you. In general, they're super noisy. In particular, I wanted to highlight three of them because they're the three more important coefficients when we have a lot of data, where the estimate, if you don't remember, I'll remind you, the estimate there is best. And it corresponds to places that have similar climates as Yosemite, which are in Colorado and Wyoming. Okay, so this is what happens at the end. Okay, these are the coefficients that we see at the end. Maybe I'll use another color. I'll use green. These are the coefficients that we see at the end. And these are the three most important coefficients. And again, they make sense. What happens at the beginning? What happens at the beginning is that we see huge coefficients, which make no sense in the sense that, I mean, look at the variations, for example, in the red line or the black line. Like, they're completely all over the place. What is happening is that we see huge positive coefficients and huge negative coefficients. Okay, so again, huge positive coefficients and huge negative coefficients. There's a lot of cancellations. This is typical of overfitting in linear models, where if you try to fit the noise, so this would be a good moment, if you haven't checked out the video on training and test error, to go back there and check it out. So we saw that when you do ordinary least squares, if you don't have enough data, so here we have very little data, you tend to overfit the training error, the training data, which means that you're kind of fitting the noise that is present in the training data. That is going to be difficult to do because it doesn't follow a linear model. In order to achieve it, what you need to do is you have these huge coefficients that kind of cancel each other out in subtle ways, and that's how you manage to fit the noise. And this is an important consequence of overfitting, that you get these huge coefficients. To summarize, overfitting is often reflected in large coefficients that cancel out to match the noise. A possible solution is to penalize large norm solutions when fitting the model during training. So basically, you're telling the model, fit this data, but you can't use huge coefficients because I don't want you to, because we don't expect huge coefficients that have to cancel each other out. If you get huge coefficients, that's probably because you're overfitting the noise. Having a penalty term to promote certain properties, in this case not having huge coefficients, is called regularization, and that's the topic of this lecture. This type of regularization that we're going to focus on here is ridge regression. And the idea is very simple. You add a term to your cost function which penalizes the squared L2 norm of the coefficient. And this is scaled by what we call a regularization parameter, lambda, which is positive, that essentially balances between fitting the data well and having small coefficients is possible. If you set a lambda very, very small, what are you going to obtain? So, pause the video if necessary, but think what are the coefficients, the ridge regression coefficient is going to be equal to if we set the regularization parameter almost to 0. Well, you're only left with this part, so they're going to be very similar to the OLS coefficients. They should say OLS. What happens when the regularization parameter is super, super large? Think about it. What happens is that the second term dominates. You don't care about fitting. You just want to make the coefficients as small as possible, so you end up with coefficients that are equal to 0. Okay. Now, in order to analyze the rich regression estimates, we realize that at the end of the day, if you can write the rich regression estimate as the solution to a least squares problem. Why? Because when you look at this cost function, you can write it exactly like this. Okay, because what's going to happen here you're going to have y minus x transpose beta in the first entry when you put all of this together, and you're going to have lambda beta in the second entry. And if you take the squared L2 norm of this is just the sum of the squared 2 norm of this, which is the least squares part of the cost function, and the squared L2 norm of this is just going to be lambda times the squared L2 norm of beta, which is exactly the rich regression component. So we can expand this least squares, we can express, the solution to this least squares problem using the closed form solution that we already derived in general. And remember that this was x transpose inverse times x. Okay, now instead of x, we have this matrix, which is x square root of lambda I. So we just plug it in, and this is what we get. And when we expand this out, we discover that essentially we get the same solutions and in ordinary least squares, except that here we're adding lambda to the diagonals of the sample covariance matrix. Okay, so in a way, you can almost think of this as almost preconditioning the sample covariance matrix by adding stuff to its diagonals. Okay, that's kind of like a numerical linear algebra if you want interpretation of this. Okay, so in practice, we've been talking about this regularization parameter lambda, but how do I set lambda? Think about this. Should we choose lambda so that we have the best fit in the training set? Think about it for a moment and think about what lambda we would obtain in this way. Okay, so if we did that, basically we would want, we would obtain the lambda that gives us the best fit, and we know that that's going to be the ordinary least squares error, because the best fit can be obtained by not constraining the coefficients at all, right? So that's going to be a lambda equal to 0. That's always going to give you the best fit. Instead, what we want is to generalize while having small coefficients, and the best way to check whether you generalize is just to have some held out data and see how well you're generalizing. Okay, so that's what you should really do. You should look at your validation data. Most of you are probably familiar with this concept, but cross-validation, or using validation to set hyperparameters such as regularization parameters works in the following way. You have a set of examples, n examples, let's say. You partition those, maybe let's like this. You're going to use some for training. Oops, sorry, my handwriting is out of control there. Training, and some for validation. Okay, and the idea is that you fit the model using only the training, and then you evaluate the model on a validation set, and you do that for every lambda. So for every lambda, you train only minimizing the cost function on your training data, and then you check the error on your validation data, and you do that for many, many values of lambda. And eventually you choose the lambda that is best on the validation. So let me show you a graph where we have used n equals to 202 in the temperature data set. So that's the number of training data. And this is what the training error curve looks like. And as I was saying before, if you just look at training error, you're always going to pick the smallest possible lambda, because that smallest possible lambda gives you the best fit by definition, because at that point you don't care about this extra term that is penalizing the large coefficients. The issue is that that doesn't generalize at all, and you get a huge validation error. Okay, you don't want to pick lambda too large, because if you pick lambda too large, what is happening? You're putting the coefficients, you're using coefficients that are too small to even fit the data in a way that generalizes. You're just setting basically the coefficients to 0. You need to find somewhere in between where you get good generalization, and the way to check that is with this held out data. This is what happens to the coefficients of the ordinary least square, the ridge regression estimate for the temperature example when we change the regularization parameter. Okay, we're again fixing n equals to 202, and what you can observe is a little bit what I just said. So if the regularization parameter is too small, we have this least square situation where there's these weird cancellations that fit the noise but do not produce a generalizable model. If you put lambda too large, then what happens is that your coefficients shrink too much and you cannot fit anymore. And then there's this sweet spot in between where you're producing a reasonable linear model that generalizes quite well. Now I'm showing you the ridge regression coefficients for lots of values of the training data, and this is for lambdas that have been chosen through cross-validation. And what happens is that we are able to maintain similar coefficients, at least if you look at the three top ones, over the whole training, over the whole number, like a whole range of training data numbers, which is good because this probably means that these models are reasonable in the sense that their coefficients have more or less the same magnitude, and the largest ones are, the most important ones are these three that we suspect are the really relevant ones because they're the most used at this part where we have the good ordinary least squares estimates. In comparison, remember the ordinary least squares coefficients here on the left were a complete mess because they were canceling each other out to try to overfit to basically overfit the noise. The regularization parameter that is chosen by cross-validation to achieve those coefficients of the ridge regression that I just showed you is typically relatively high when n is small, and when n is large, you basically don't even need to do regularization, as we know already from having seen the results for ordinary least squares, which are really good when the training data are enough. When you look at the errors and you compare least squares with ridge regression, remember, like least squares are these crosses here. Maybe I'll change the color. This is the test error of least squares. For the basically, remember that we have two test sets. One that is just held out data, and the other one which is from data from another year, which is usually more difficult to generalize to. What we see is that we have large test error for least squares, and ridge regression, thanks to this regularization, manages to overcome that and actually produce very reasonable error that is close to what ordinary least squares achieves with a lot of data, with much less data. Okay, so here ridge regression is giving you a strong advantage, and the reason it's giving you this advantage is that it prevents the model from overfitting, and you can see that in the training data, the training error. So here we're overfitting, as we had discussed in the lecture on training and test error of ordinary least squares. Ridge regression does not overfit, as much at least, and hence achieves better generalization. When you have a lot of data, it doesn't matter. Ordinary least squares is not overfitting anyway, so there's no point in doing ridge regression. Okay, so now we're going to try to understand a little bit what ridge regression actually does. And in order to do that, we're going to go back to this additive model that we had, where we have that the training data are n. So it are basically modeled as a random vector with n entries. And each entry, well, the entries are corrupted by IID Gaussian noise that we call Z-train. But otherwise, they do follow a linear model that depends on these true coefficients. So if you remember, with ordinary least squares, we had expanded this expression into two terms, this term and this other term, to basically study the coefficient error. Well, here we can do exactly the same expansion, except that we have an extra term, that is this beta transpose beta. If you remember, this expansion, you can just check it again on your own, or look at the video on the coefficient error of ordinary least squares. but we're deliberately ignoring every term in that expression that does not depend on beta, okay? Okay, so we have this cost function now. If you remember, this term here, this is just a quadratic with beta true at the center. So if we only had this term, we would achieve perfect estimation because we would have a quadratic that has its minimum exactly at the truth, at beta true, okay? Now this other term that we add here, this other term is just a quadratic that is centered at 0, okay? It's beta transpose beta. The contour lines here are just spheres around the center. When we combine both, we have moved, so basically when we use sum two quadratics, you get a quadratic. So this is a quadratic function. Now the quadratic function is not centered at either 0 or at beta true. It's centered in between. Okay, and we call this beta bias because, as we'll see in a moment, because of this combination, we're going to have a systematic bias, a systematic error in the coefficient estimate of ridge regression because we have added this guy. The other term, okay, the other term that we haven't added yet is this noisy term, which, if you remember, corresponds to just like a linear term that is in random directions because this is the noise. That gets added up so that you end up with this, so with a quadratic that has a minimum somewhere else, right? It's not at beta bias, which is without this term. It's somewhere else. And depending on the realization of the noise, it can change. So realize that here, we are also writing the, we're also showing you the ordinary least squares. So both the ordinary least squares and the ridge regression changes, beta true and beta bias stay the same, okay? These are not random, but the solution to ordinary least squares and the solution to the ridge regression change all over the place because of this random term. The difference between ordinary least squares and ridge regression is that we have this term in the quadratic function. And now we're going to try to understand how that term influences the form of the quadratic function. Okay, that's the idea. Okay, so remember that we have derived that the ridge regression coefficient estimate is equal to this matrix times the features. And the features we are going to assume can be written like this, okay, the training features. So now when we put this together, we're going to, as usual, use the SVD all over the place. And we're going to use this trick that we can expand I in terms of UU transpose because this is going to be very useful. We can, of course, expand the identity in terms of any orthogonal matrix, but here we're going to use the left singular values of X because it's going to be really useful. Here, again, we're applying XX transpose is just equal to US squared U transpose. And here we're applying just this is the SVD of X, okay? Now we're going to collapse everything. Here we do this trick where we can take UU transpose out in order to take the inverse. Okay, here we're taking UU transpose out. The inverse is equal to that. Again, like here there's perhaps the steps are going to get, a bit intricate at some points. I recommend that you follow them through slowly and you ask us if you have any questions. But at the end of the day, it's basically about using the properties of orthogonal matrices. So in particular, if you have U here, whatever, like a diagonal matrix U transpose, and you invert this is just equal to U D minus 1 U transpose for a diagonal matrix, and you can check that, and this is this step here. What we end up with is two terms. One that depends on beta true and one that depends on Z train, okay? Here, I've written the two terms again, and we're going to ask ourselves, what is the distribution of the coefficients of ridge regression? Okay, the distribution here, this is a deterministic term because it doesn't depend on the noise, and this is a random term. The random term, if you realize, depends on this Gaussian vector that is IID and has zero mean. This immediately implies that the mean of the coefficients is just equal to is equal to this vector. Okay, so beta bias, which is, I mean, we'll see in a moment why we call it bias. It is this vector that we can expand in this way, and the variance, the covariance matrix, of this can be obtained by taking, so this is equal to a C train for this matrix A, and the covariance matrix is going to be equal to A transpose. So you just need to expand that, and this is what you get. Okay, again, it might look a little bit complicated, but we're going to talk about it intuitively in a moment. So let's look at the two terms separately, again, slowly. Like, I realize that these are pretty complicated expressions, but let's go about it slowly. We have, again, a deterministic term that depends on beta true, and we have a random term that does not depend on beta true, it only depends on the noise. And now we're going to see how these terms, what are the properties of these terms when lambda changes. Okay, so the first term, as we will see, produces a systematic error, because when we do beta true minus the Ridge regression estimate, what happens is that this guy is going to have zero mean, so this guy is going to disappear. So we end up with this expression, where again, this guy that depends on the training noise is going to disappear because that's zero mean. So we end up with this expression. Okay. Again, where does this come from? We have taken this guy and we subtract beta true. Or rather, we take beta true and we subtract that guy, and this is what we obtain. You can check, again, the actual values don't matter too much. You can check them. The detailed calculations are in the notes, and you can ask us questions. But the point here is that this bias, this systematic error, so on average, the average error actually grows with lambda. So essentially, what I'm saying is that first term that depends on beta true, you don't want it there. And it makes sense, right? Because if you remember, with ordinary least squares, it was actually not there. So if you only care about that term, about this systematic error, then you want to just put lambda to 0. So what's the point? Why do we have a lambda? How is this helping? Well, it has to help with the second term that basically is responsible for the variance. So again, I'm going to go back for a moment. This expression might seem a bit complicated, but essentially what it's telling us is that the variance in the directions of ui is equal to, or uj, let's say, is equal to sj squared, so this thing in the center, right? Like, this is the variance in the direction of each of the uj's. And this is exactly what it's saying. Oh, I forgot to mention, I'm sorry about that, that this diag means that this is a diagonal matrix that has these entries in the diagonal. Okay, I know again that these formulas take quite a bit to digest, so what I really recommend is that on the one hand you follow the derivations by hand, but on the other hand, now we're talking about the intuition. So try to absorb the intuition and understand that intuition, and then you can confirm that what I'm saying is true, but by going through the computations by hand. But the important thing here is the intuition. So okay, so this is basically telling you that your variance in every direction is sj in the direction of the jth left singular vector of the covariance matrix is equal to sj squared over sj squared plus lambda squared. Okay. So let's go back. Okay, so it's telling us that this is the variance in each of those directions. Now that variance, as you can see, decreases with lambda. Okay, so if a small value, and remember that for ordinary least squares, okay, and which you can see by basically setting this guy to 0, in ordinary least squares, the variance is sigma squared over SI squared. So if SI is very, very small, boom, like this explodes. Okay, that's this huge coefficient errors that we observed when we were looking at the coefficients, even in our real world example, when we didn't have enough data. Okay, so if lambda is very, very large, is large with respect to the smallest singular value, then the variance is going to be equal to, so here lambda is going to dominate, and you're going to end up with a lambda that is sigma squared times SI squared over lambda squared, which is small. So you have managed to cancel this variance coming from the small singular values. Of course, you don't want lambda too large, because then you are going to have a huge bias. Okay, this is basically equivalent to setting just the coefficients to 0. But if lambda is just large enough to cancel these small singular values, you're going to be able to control the variance and hopefully not increase the bias too much. And that's what is called achieving a bias variance trade-off. Now we're going to look at an example where we have in this that the like we have a covariance matrix that follows a simple example that we used already to analyze ordinary least squares, where in one direction, in this direction in particular, it turns out that we have a very small singular value. Okay, and here the singular vectors are aligned with the axis just to make our life easy. When we look at the estimate for the coefficients, for small lambdas, which is what we would observe also for ordinary least squares, we have a lot of variance. So these are different realizations of the data. And what we see is that the estimates that we obtain are all over the place in that direction because we have a small singular value. So that's the error is exploding in that direction. And if we start increasing lambda, what happens is that we reduce the variance quite a lot. By the way, here, the error, like you can see that this is more or less centered around beta true. So indeed, actually I've forgotten some points there on to the right. Like this is more or less centered around beta true. So it is unbiased. Like on average, the error is not that large, but there's a huge variance. So very often we're very far. So huge variance, no bias. But on the whole, a pretty terrible estimate because most of the time we're very far. Here we have biased ourselves. So our center is more or less here. So there is a bias when lambda is larger, but we have reduced the variance a lot. Of course, if we reduce the variance too much by setting lambda too large, boom, we have too large of a bias, and this is not ideal either. So probably this is best from the point of view of minimizing the bias variance trade-off. Okay, and this is a picture of the actual distribution. Again, when lambda is small, we have a small bias but a huge variance. And in the limit where lambda is 0, we recover the ordinary least squares solution where the variance is just huge. And as lambda grows, the variance is reduced, but the bias increases. Okay, because basically this point goes towards 0. So what have we learned? We have learned that rich regression prevents overfitting by penalizing large linear coefficients when we're fitting a linear model. We have learned that this produces a biased estimate, so you're going to start having a systematic error on average. At least when you analyze this under a linear data model with additive noise, but as we have seen, this actually kind of gives you good insights into what you observe with real-world data. And the regularization parameter balances between having this biased estimate, because the coefficients are essentially pushed towards 0, and reducing the variance in the coefficient that comes from the small singular values in the feature matrix. And that's it. Thank you very much.